Yeah, started? Okay, thank you. Yeah, make sure that the phone doesn't die while we're recording. Yeah, so good afternoon, everyone. Yeah, so we are starting the so-called second part of the course today, but still the first part of the book, very much. Right, so the book has 12 chapters in part 1, and we are starting chapter 8. So please remind me at 5:45. I want to stop by 5:50. Yeah, so I was trying to rationalize sort of these two parts. Like I was trying to figure out how to exactly fit them in the larger context of graph theory, right? So in graph theory, two very important operations are deletion and contraction. I mean, one could argue that these are, in structural graph theory, these are some of the most important operations out there: deletion of edges and contraction of edges. And then I was thinking, the first part, I mean, of course, contracting an edge in a matching covered graph doesn't make any sense, because then you don't even have an even number of vertices. So contracting an edge is just kind of pointless. But in some sense, the first part of the course is the contraction part of the course. You contract not an edge because, well, you want a matching covered graph. You contract the shore of a separating cut. By definition, you have a matching covered graph. And a special case of that is tight cuts, in which case, of course, you get very nice theorems like Lovaas's uniqueness theorem, right? So in some sense, contracting or shrinking a set of vertices, which is, you can simulate shrinking a set of vertices by contracting edges, assuming that set induces a connected subgraph. If you just contract all the edges in that set, then you will basically simulate shrinking the set of vertices into a single vertex. So in some sense, the first part of the course is the so-called contraction part, and the next part is actually about deletion. But just like in contraction, you can't contract just an edge. Here you can't just delete an edge unless you get a matching covered graph. So yeah, and then I realized while I was reading chapter 8, this is exactly how they explain it. They actually say that shrinking the shore of a separating cut, or more specifically of a tight cut, is like contraction, and the second part is about deletion. So turns out my own rationalization coincides with theirs. So I was kind of happy to see that. Okay, anyways. So therefore, we begin part 2 of this course. But as I said, it is still part 1 of Lucchesi-Murty. Okay. So one of the main results in part 1 of the course was Lovaas's uniqueness result, right? Uniqueness of the tight cut decomposition procedure. The fact that you get the same list of bricks and braces up to multiplicities of edges, no matter what procedure, in what way you choose tight cuts, right? Doesn't matter the specific tight cuts you choose. In the same spirit, there is a main result in this part also. It's a so-called ear decomposition theory of matching covered graphs. So I would like to, this is one of the main results. But this will come much later. Except that one part of it has already appeared. We already know from SGT the ear decomposition result for bipartite matching covered graphs. In fact, that is covered in Lucchesi-Murty, I believe in chapter 3, in the same chapter where the canonical partition theorem is proved. although we kind of skipped it because we've already done it in SGT, right? But if you want to construct non-bipartite matching covered graphs, right? So ear decomposition is something we are all familiar with because we spent a hell lot of time on that in SGT, right? So that is ear decomposition theorem for two connected graphs or non-separable graphs, almost the same thing, right? So there are similar results for matching covered graphs. One is the bipartite ear decomposition theorem. Let's just remind ourselves what that says, right? Let's just remind ourselves through an example. If you want to construct the cube, you can do that by simply adding ears of odd length joining white vertices to black vertices. This would be my first ear, this could be my second ear, this is my third ear, this is my fourth ear. And in fact, the converse is also true. Any graph you generate like this, you start with an even cycle, and at each step you introduce a new path, also known as ear. You add a new ear of odd length joining a white vertex to a black vertex. Then the graph you will get will be bipartite matching covered, and it's both ways, right? In the case of non-bipartite matching covered graphs, it won't be both ways. I'm not going to give you the formal statement today. That will come much later. But what we will do is we will just construct the Peterson graph as an example. Okay? But before we go to Peterson, let's do something much simpler, K4. You can start with an even cycle, and there is basically only one even cycle up to symmetry. That's C4. Let's color the vertices, that is instructive. I want to go from here to K4 by adding ears. As you can see, this is not possible. If I just add a single ear, a path of odd length, because I want an even number of vertices, well, I already have all the vertices anyways. Right? If I just have to add a path of odd length, then I would add one joining this white vertex to this white vertex, or this one to this one. Doesn't really matter. I get C4 plus an edge, that's not matching covered. So that's not good. But what you can do is you can add both of them simultaneously. Like, what else can you do in life anyways? If you want K4, you can't get K4 minus one edge. You have K4 minus two edges. Right? So you have to do this. And now you have K4. The only thing is, we allowed ourselves to add what is called a double ear, a pair of vertex disjoint single ears, where ears are still paths of odd length. And you can also do the same thing on prism, not too difficult. Prism, and observe that if you add a path of odd length or two paths of odd length, let me make a more general figure. Supposing I add two paths of odd length, vertex disjoint simultaneously. Looks like an elephant with its ears. At least my version of an elephant. I can't draw much better than this. Right, so that's what you get. And observe that this fellow, H, is a conformal subgraph of G. G is the whole graph, and H is just this fellow. Right, maybe I should write H inside. Clearly H is conformal in G, right? Because you delete the vertices of H, remaining graph has a perfect matching. Okay? So if you want to construct triangular prism, you can start with either a 4 cycle or a 6 cycle. I will do maybe 4 cycle. Supposing I start from here, now I can add an ear. I still have a bipartite graph. At this point, I need two more edges. And you can see we are in the same problem as in K4. I add this edge, not in any perfect matching. Same with this one. So I can do both simultaneously. Right? So the result we will prove eventually in chapter 11 is that every non-bipartite matching covered graph has an ear decomposition. The only thing is, you must allow the addition of double ears Otherwise, you just cannot get any non-bipedal matching code graph, assuming you're starting from an even cycle. Right? Let's do the Peterson graph as a last example. So the point was, you need the smaller graph to be conformal. In fact, it follows that in any year decomposition, all the subgraphs will be conformal, right? Because if H is conformal in G, then by transitivity of conformality, all the graphs will be conformal. Okay, good. Now the Peterson graph, it is not Hamiltonian, as we all know. Therefore, there are only, it is also Girth 5. So the only cycles are 6 cycles and 8 cycles. You can check that if you delete a 6 cycle, vertices of a 6 cycle from the Peterson graph, you will get K13, not conformal. However, if you delete the vertices of an 8 cycle, you will get K2, conformal. So what we will do is we'll start with an 8 cycle. Okay. Let's see. Here's my 8 cycle. And the next thing we will do is we will add an year. Right, let's see. You'll add a double year. Wait a second. Yeah, let me just draw the way I kind of know how to do it. So here is a drawing of the Peterson graph. That is very useful for this purpose. Okay. Alright, so maybe I'll start from here instead. So let's try to locate an 8 cycle here. Right, there are several 8 cycles. Let's see. Yeah, but that doesn't look very good. I want this K4 minus this path. Okay. I want this is basically a K4. I want to remove these two things. Yeah. Okay, that's an 8 cycle. I can start from that 8 cycle. You can see it's conformal. You delete everything, you will get a K2. Every 8 cycle in the Peterson graph is actually the same. They're all symmetric. Now, up to symmetry, there's only one thing you can do. You can add what we call a double year. This is matching covered. It's a bi-subdivision of K4. K4 is matching covered. We know that every bi-subdivision of a matching covered graph is matching covered. Therefore, this is matching covered. Yellow plus pink is matching covered. But we don't have the Peterson graph yet. We need to add more things. Okay, and there is no chalks here. Or there is some chalks, but they are not colorful enough. Okay. Okay, so that's one thing we can do. We have this bisubdivision of K4. We are missing 3 edges. Yeah.
Are you telling me this is the only year we can add more?
You mean from the remaining 3 edges? The next one?
No, from the yellow cycle.
From the yellow cycle. Good point. From the yellow cycle, could I have added any other year? I believe up to symmetry, this is the only one. But if you don't care about up to symmetry, there might be other possibilities. Up to symmetry, you will get exactly this bisubdivision of K4. Yeah? Now there are 3 more edges, the white edges that we need to get the Peterson graph. Convince yourself that they are all actually symmetric. They are all symmetric to each other, it's just a rotation. If you just rotate the fellow, you will get all 3 edges. And convince yourself that if you add any one of them now, the graph is not matching covered. Try to include one of those 3 white edges and observe that the included edge is not in any perfect matching. Yeah? Everybody agrees? So, however, if you include any 2 of them, then actually the graph is matching covered. So I will therefore include 2 of them. Maybe I will do yellow. This is matching covered. Check that these 2 edges belong to a perfect matching that does not use the last edge that we have not added yet. Is that true? Can everybody find a perfect matching containing the 2 yellow, curvy yellow edges but not containing this white edge? Yeah? And now you want the Peterson graph, well, you'll add the last edge. Right? And that's matching covered. It's a 2 connected cubic graph, therefore it's matching covered. Then it's Peterson. Okay? So here is an ER decomposition of the Peterson graph. We had to add double ears twice. The first time we added the double ear, we got a bisubdivision of K4. And the second time we added a double ear, we got the Peterson graph minus 1 edge, which is uniquely defined because Peterson graph is very nice. Right? Okay? So this is sort of one of the main results we will get to, right? And the original results of the original proof of this theorem, I think it is the one in Lowas and Plummer, it directly deals with ears. What Carola, Lucchesi-Murty have done over the years is they have found other ways of proving these results, and in fact in the process they have proved way stronger results for many of the results that were already known. We will see examples of this. So the idea is, let's not worry about ears, let's just focus on edges, and then we will get all the ear decomposition results as corollaries of the so-called edge results. Yeah? And that's what we are going to do next. We are going to focus on edges of a matching code graph, right? And when can we delete them, etc., etc. Yeah? Are there any questions or concerns? Okay, so let me get rid of the ear decomposition theory stuff. Okay, so an edge E of a matching covered graph G is removable if G minus E is also matching covered. Right? This is the kind of edge we are allowed to delete. We can't delete other edges. In the same spirit, we will say that a set R is a removable set if G minus R is matching covered, a set of edges. empty set R Notice that there is no other condition. We are just saying whether the set is removable or not. So you delete all the edges in that set. Do you have a matching code graph or not? For example, in the case of the Peterson graph, we had a bisubdivision of K4 and then we were missing 3 edges. Well, those 3 edges, it's a removable set. Right? In this spirit. Okay? Of course, what will be more interesting is not just any removable set, but a minimal removable set. In the case of the Peterson graph, those 3 edges, they are not a minimal removable set. I could have just deleted one edge from the Peterson graph and I would still have a matching code graph. So, not minimal. Okay, what about bipartite graphs? Can we say anything about minimal removable sets in a bipartite matching code graph? What can we say about minimal removable sets? In bipartite matching covered graphs. Think about it. Of course, if it exists. If it doesn't exist, then well, you don't say anything. Right? Supposing you have a minimal removable set, right? Then what can you say about such a set? Okay, I'll walk around. So I'll make the question more concrete. How large can the set be? If I tell you I have a bipartite matching code graph and I have a minimal removable set, can it be large? Can it have 10 edges? Can it have 5 edges? Can it have 2 edges? Stuff like that. And think about all the characterizations of bipartite matching code graphs that you already know. The answer lies in there. Yeah, note that the definition of removable in the case of a set of edges is it's non-empty. Right? So suppose you have a minimal removable set of cardinality 2, and you get some contradiction. You remove the two edges, you have a bipartite matching covered graph. Right, so recall that in a bipartite matching covered graph, if you delete a black vertex and a white vertex, you still have a graph that is a perfect matching. That means that if you add an edge joining a black vertex to a white vertex, you have a matching covered graph. Right? So if you could delete two edges E and F from a bipartite matching covered graph to get another bipartite matching covered graph, well, you can add back E, and it is still bipartite matching covered graph. Therefore, E comma F was not minimal to begin with. Right? So therefore, the same argument essentially proves that every such set has cardinality 1. If it exists. It doesn't have to exist. And even cycle on 4 or more vertices has no such set of edges. That's okay. So what? Right? So 8.1, they call it a theorem. I want to call it a corollary. I'll just forget it. 8.1, whatever. Right? We are far enough in the course, this doesn't matter. When something is really non-trivial, I'll call it a theorem. But of course, non-trivial depends on how much theory you've already seen. So, in a bipartite matching covered graph, every minimal removable set is a singleton. Yeah, follows from things you've discussed before. Yeah. Okay. So that's nice. Going back to the ear decomposition, remember we said that we will prove a result where either you can add a single ear or you can add a double ear, 2 ears simultaneously. In the same spirit, one of the results we will prove is for matching covered graphs. If you forget bipartite, we will actually prove that every minimal removable set is either a singleton or a doubleton. Soon. Maybe next lecture, maybe next to next lecture, I don't know. But we'll prove this soon. Right? So in general, for a matching code graph, it need not be singleton. K4 is an example, clearly. But turns out it's either singleton or doubleton. You can't have a larger set that is minimal. Yeah, okay. So this is one of the results that is coming up. And this is basically related to the same year decomposition phenomenon. Okay? Good. So now let's talk about the doubleton case. Since doubletons are actually going to play an important role, let's define a removable doubleton. By a removable doubleton of a matching code graph, we mean exactly this. We mean a pair of edges, E comma F. This is a subset of the edge set, such that G minus E and G minus F are not matching covered. But G minus E minus F is matching covered. Right? Of course, you can define a removable tripleton, but that won't be very useful because of the result we will be proving. So we will not define tripleton, and we'll stop at doubleton. Okay? So that's what a removable doubleton is. In K4, every perfect matching, the two edges, they comprise a removable doubleton. In the triangular prism, you take one edge from this triangle and you take the corresponding edge from this triangle, that's a removable doubleton. Now by symmetry you can see that in the triangular prism there are three removable doubletons. Yeah, and so on. Okay, what's next? So let's discuss about non-removable edges in bipartite matching code graphs. Let's try to figure out a characterization of non-removable edges in bipartite matching code graphs. Basically, at this point in the course, most things about bipartite matching code graphs are just easy based on things you've already seen. Okay, so that's the next point. Can you try it yourself? Can you try to figure out what would non-removable edges in bipartite matching code graphs look like? See if you can make one example. Don't give me cycles, that's very easy. Give me more complicated, right? So why is an edge not removable? Right. So consider G, AB to be your bipartite matching code graph. Consider E, little a, little b to be a non-removable edge. There, of course, A belongs to A and B belongs to B. Then what can you say about G minus E? What does it look like? And based on that, what can you say about G? Like typically for bipartite stuff, you should get this N shape kind of drawing, or something close to N shape. There is one. Let us observe that G minus E is matchable, except for, I claim that G minus E is always matchable. There is one exception, K2. Except for K2, you delete an edge, take an adjacent edge, that is in a perfect matching, so graph still has a perfect matching. That would not be possible if the graph is K2 because there is no adjacent edge. Okay. So clearly, yeah, so let's actually remove K2. In general, with bipartite graphs, it helps to remove K2. So then G minus E is matchable. But because it is non-removable, it is not matching covered. So you have a bipartite graph, clearly the graph is bipartite, original graph is bipartite. You have a bipartite graph, you have deleted one edge, you have a matchable bipartite graph that is not matching covered. Now try to apply things you already know. What does a bipartite graph that is matchable but not matching covered, what does it look like? Okay, so maybe I'll just oops, sorry. Right, so you have a matchable graph that is not matching covered. Well, bipartite graph is not matching covered. That means that there is a non-empty subset of the white vertices whose neighborhood is not big enough. It is not one bigger. If for every set it was one bigger, then the graph would be matching covered, right? So therefore there has to be a set for which the neighborhood is not one bigger. It can also not be too small because the graph is matchable. It has to be equal, right? So what you get is that there is some set in G minus E whose neighborhood is the same as its cardinality, right? So supposing this is my set S, this is the neighborhood of S in G minus E, and this is not the whole set, so therefore there is more vertices here. This is my A, this is my B, some of you are drawing the majority minority figure. That's a bit, yeah, it's kind of close but not quite the same, right? So what you want is actually, you will get an even cut, not an odd cut, right? If you are doing majority minority, you will actually have an odd cut, right? So you have some set whose neighborhood in G minus E is equal to its own cardinality, right? So in G minus E, all the edges have to go like this, and like this in G minus E. There could be many edges like this, and like this, and like that. But there are no edges like this in G minus E. In G minus E. Yeah? So you got the end shape in G minus E. Now the question is, where is E? Well, if you include E, then the graph is matching covered. For that, E must go like this, because otherwise these edges will not be in any perfect matching. And there should be some edges like this, because matching covered includes connected. Never forget that. When dealing with removable edges, keep in mind, you need the graph to be connected. Right? That's part of the definition of matching covered. So therefore the edge E goes like this. It is the only edge in G that goes from here to here. And we don't know how many edges are like this, that doesn't matter. But all the other edges are like this. Right? This is the only one like this. And what they will do is they will call such a set a certificate of non-removability of the edge E. I'll write down the definition next time. But this is basically the corresponding cut actually. I think they refer to the cut. Certificate of non-removability of E. Yeah. Okay, so that's about it for today. I want you to think about what about braces. TIY. What can you say about removable edges in braces? Okay, so we'll continue next time about bipartite matching curve graphs. There's a very nice result that is coming up. Instead of certifying just one non-removable edge, there is a result by Lowas and Vempala where you certify a bunch of edges incident at a vertex to be non-removable at the same time. So there is a very nice drawing, just like this drawing. It turns out there is a generalization of this that certifies the non-removability of several edges incident at a common vertex. And that result is used later in a lot of places. And I think recently Ravindra might have used it in his research. Right? Lowas Vempala. Yeah. Okay? And in general I have found it to be very useful in life. So we'll talk about that and then we'll continue. But one of the main goals of this chapter is to get to this result. Every minimal removable set in any matching code graph is either a singleton or a doubleton. But we'll take some time to get there. Yeah. Okay, thank you. That's all for today. And we continue on Wednesday. Thank you.